Hi Mrs. Dags. Well, I'm back for the last and final time. Final project. This is the last one. Now I'm not gonna say that this was the easiest project. In fact, I would say that I almost went insane doing it. I'm not even joking. This past Sunday, when I finished the project, my right eye kept twitching for the rest of the day. It was insane. Even with that being said, I learned a lot. This was a really informative and actually really interesting project that I did. And I kind of enjoyed learning about this type of stuff. Now, if you ever see me looking down or glancing down, I should be able to edit it out, the most of the looking down. But if you ever see me looking down, it's because I have my notes here. And I sent you a copy of these notes just in case you want to look back at my math and stuff that's in there. I think when I turned it in when I finished doing my notes and math. So I think I labeled it not final project, just turning in so I don't forget, something like that. So it's going to be turned in before this video is turned in, so you can go back and look at it for my work. Well, I'm going to start at step 1, because generally that is where you start. Though this was actually one of the hardest steps that I did through this thing. For the life of me, I could not find the exact power needs, electrical power needs, of each city. I couldn't do it. I looked everywhere. Atlanta was especially impossible to find. I even brought my stepdad in, who is an engineer, and he still couldn't find anything or figure anything out. So I got a little innovative. What I did was I took the electrical power needs of every household in the state the city was in. So for LA, I would find the power needs of each household roughly in California, or Atlanta and Georgia, Illinois, Chicago, and so on. Well, I guess New York's the only one left, but and so on. And then I found how many households was in each city. When I found that, I just multiply the numbers together, bada bing, bada boom. You got your number, roughly. I know it's not going to be anywhere near the exact number, but it gives a good rough estimate, especially since I couldn't find everything. So now I'm going to be looking at the notes, which I have the numbers for. So for New York, there's approximately 3 million households. In Atlanta, there's 220,000 households. Chicago, 1 million households. Los Angeles, 1,400,000 households. In New York, each household takes about 602 kilowatts per month. In Atlanta, 1,088 kilowatts per month. In Chicago, 755 kilowatts per month, and in Los Angeles, 551 kilowatts per month. Now remember, I have all the notes turned in, so I know I'm kind of rambling with these numbers, so you can just go back and take a look at them in depth. With that being said, the rough electrical power needs of New York City is about 24,352.55 gigawatt hours per year. Atlanta has approximately 2,934.55 gigawatt hours per year. Chicago has about 10,820.69 gigawatt hours per year. And Los Angeles has an approximate electrical power needs of about 9,349.33 gigawatt hours per year. I know those aren't going to be exactly right, and I also have the per month and per day numbers on this sheet, which you can also look at. So I'm just going to stop saying you can go look at it, because you know you can go look at it. So just take a look at them if you need them. Step 2 was a lot easier and less complicated and less work than I had to do for step 1. There was one website that had exactly what I was looking for, and it was perfect. So for step 2, we needed to find the amount of solar energy received in each city and at their longitude and latitude. So first I found the longitude and latitudes of each city and then calculated what the approximate solar energy received at that place was for a couple months. So like January and March and May, maybe like September. So I just found a couple months, and then I just found an average per year. So with New York City being at about 40.71 degrees north, 74.01 degrees west, they had an average of 3.95 kilowatt hours per meter squared per day. And they also had an average of 2,535 hours of sunlight per year, which does come later when it comes to the photovoltaic cells. And so I also need to find those, which I did. For Atlanta, they have an approximate 5.12 kilowatt hours per meter squared per day and 2,738 hours of sunlight per year. Chicago had approximately 4.13 kilowatt hours per meter squared per day and about 2,508 hours of sunlight per year. And Los Angeles finally has an average of 5.5 kilowatt per hours per meter per year. Geez, a mouthful. And 3,348 hours of sunlight per year, which is the highest by a long shot. Oh, and I also forgot to mention that Atlanta is at about 33 degrees north, 84 degrees west. Chicago's at about 41 degrees north, 87 degrees west. And Los Angeles is at 34 degrees north, 118 degrees west. Now, solar concentrating power plants was one of the two types of solar power collecting that I researched, which I will now be referring as CSP from now on. I'll start off by stating what CSP really is. So CSP is a type of solar power that uses mirrors to reflect on a receiver. And it reflects all that sunlight and focuses it on one place. Now, when the light hits the receiver, it heats up the full thing of molten salt. When this is needed, it flows to a storage tank until it's needed. There is also a water tank in this area as well, nowhere specific it needs to be. But when power is needed, the molten salt and the water is flowed into one area. The molten salt heats up the water, creating steam, which flows to a steam generator, and which makes a turbine spin, creating energy. That's the rough usage of how these things work. There are some variations of this technique, but that is the very rough and cut version of it. Now, there are technically 5 different types of CSP plants that I could find, but it really only is 4, so I'll tell you what those are about. For each of these, I'm also going to include a little picture right here, or somewhere on the screen, that I drew myself, the wonderful artist I am, as you know from previous projects. In each of the pictures, I have in black pen where the receiver is. There's faint lines, what the sunlight is, and then just like the random boxes places are the mirrors. I also have them labeled on there so you can just see there. A parabolic trough is the first type of CSP that I learned about. It is also the most developed type and the most commonly used. Later, when I get into which would be better to use, PV cells or CSP, I will be using parabolic troughs as my general CSP. So that's like the main thing that we use. As you can see on screen now, a parabolic trough is a bent mirror, kind of, where when the sun hits it, it bounces off and then hits a pipe in the middle of it. So it hits it, and in a parabola, there is one focal point, so where if you throw something, hypothetically, in a perfect straight line, when it bounces off, it will always hit that focal point. So what they did was they put the mirror in the shape of a parabola and put the collector at the focal point. So when light hit it, it would always bounce into that one place. This became very effective. There is also another type of parabolic trough that this is what I consider as still the original, but it's just a modified version. This is the enclosed parabolic trough. And it's just like in a greenhouse sort of thing, so the light comes in and it doesn't really go out, so it's just very hot in there. And they're used some places, but not very popular. A solar powered tower, that's very rhymey. A solar power tower is the second most known and used type of CSP. What it uses is hundreds or even thousands of mirrors, just regular flat mirrors, pointed at one tower, one collection cell where all the mirrors, they hit that one cell on the top of the tower, and then it goes and does its thing. It's a lot more simple and probably one of the earliest types of CSP. Fresnel reflection is also down there with the enclosed parabolic troughs, as they are not used or commonly talked about. They're kind of a combination of the solar power tower and the parabolic trough. They use a pipe like a parabolic trough, and they use hundreds of mirrors, or thousands, around it, much like a solar power tower. So they all hit the mirrors and they all come together at that one little pipe and heat up the salt, and then it goes. A dish Stirling is kind of what you picture when you think about solar power concentrated. It's pretty much just a dish, so you would almost a bowl, and it's really a parabola just circled around. So it's a 3D parabola that it's like a spinning 3D parabola. And so once again, they put a receiver in the focal point of that parabola. The sunlight hits it and goes in the receiver, and then it does its thing. The second type of solar power energy that I looked up was photovoltaic cells, which I will also, much like the CSP, I will refer as PV cells from this point on, because see, can't even do it now. Photovoltaic is a mouthful, and PV is what is most commonly known as. PV cells are what you think of when you think of solar power in your average city. It's what you think of when you're in third grade science and you put a little solar panel onto a little toy car to make it run. It's pretty much a rectangle with all these little cells, and the cells is what I'll be getting in depth to. PV cells are made out of modified silicon. Silicon is a semiconductor, and it is also the second most abundant thing on the periodic table in the world. In these photovoltaic cells, there are a couple of layers. There is a backing layer, then there is a silicon wafer, and then there is conducting material and a glass layer on top. I will have a picture of this as well as in my notes. When sunlight hits the cells in silicon, it creates a flow of electrons called the photovoltaic effect. For PV cells, they are modified to harness this PV effect, and modified so exactly so it's perfect for solar energy. When we make the silicon, when we modify it, we make impurities so it has both an N side and a P side. I will have a picture of this up on the screen as well. On the P side, some silicon atoms are replaced with boron atoms. Boron atoms have one less electron than silicon atoms do, and it leaves a hole where the last electron should be. Now on the N side, some silicon atoms are replaced with phosphorus atoms. With phosphorus, they have one more electron than silicon atoms do. So this creates a little crowded. It's crowded. So naturally, what wants to happen is the boron atoms need an electron, and the phosphorus atoms need to get rid of an electron. So obviously, the electrons flow and try to get to the boron atoms from the phosphorus ones. When the electron leaves the phosphorus atom, it creates a positive charge. And when it comes and goes into the boron atoms, it brings along with it a negative charge. As this happens, an electric field is created in the junction between the P side and the N side. This is commonly known as the depletion zone. Now when light hits the N side, it will create the photovoltaic effect and will knock electrons loose, creating a little negative charge that's floating around trying to find a positive hole to go in. Normally, as I said before, it will go to the P side. But now, with the depletion zone, there's a wall of negatively charged area where the boron atoms were filled, where the holes were filled. So, it bounces back. Normally, it wouldn't have anywhere to go, because now it's just stuck perpetually in this one little area with nowhere to go except for to fill little holes, and that can take a while. It really wants to get to the P side. So, us humans, as smart as we are, we gave it an extra route. An external circuit, if you will. They connect this to the N side, and it goes all the way to the P side at the bottom. So, when they are knocked loose, they will take that circuit, and when they take this circuit, it creates an electrical charge. So what we do is we put a device in the middle of the circuit. So when it's flowing through, it gives that thing energy, and then it goes through and goes to the P side, and then it's all good. So generally, we aren't just waiting for the sun to power things. So what we do is we put batteries there. So it goes into the battery and stores that energy. For step 5, I'm going to be looking down at my notes a lot because there's a lot of numbers and a lot of things to get through. So what I found was that there was enough solar energy to fill every single city that I researched with both type of power cells. But it's just a matter of how many types of things you use. So it's all a matter of space. So what I did was I went and I looked at how many square meters each city was. For CSP, it was a little tricky to find the average usage of it and the power. So there was no exact website. So what I did, had to get a little innovative, kind of like in step 1, and what I did was I went through a bunch, and by a bunch I mean like 3 or 4 or 5, of different types of CSP plants around the world. And I found the average size and average amount of power they use. Like I said, I'm going to be using a parabolic trough as our main use of CSP. And with a little calculations, I found that on average, there is 213.80 watt hours per year per watt hours per meter squared per year. That's a mouthful, I know. But it all makes sense. And with my findings of watt hours per year per watt hours per meter squared per year, I also found the average cost in dollars per meter squared. Very approximate. They were all very different, but I did find a good medium of what it was. And I found that to make an approximate CSP was about $200 per meter squared. That doesn't sound like a lot, but once you get into the high numbers that I found, it is huge. I found that if in New York we need 24,000 gigawatt hours per year, we are going to need, big numbers, 559,395,705.4 meters squared of land just in New York for CSP. That's a very big number. Now when it comes to cost, I calculated the approximate installation cost, so I found that, and the approximate kilowatt hours per year that it would cost, so dollars per kilowatt hour per year. And all these numbers were between the year of 2010 and 2015. So it's not today's numbers, it's not 1998's numbers, it's between the years of 2010 and 2015. I thought I might mention that. To make about 560 million meters squared of land, it would cost us about 111,879,141,080 just for the construction of this. Per year, it would be about $3,409,357,000 per year. That's per year. We have to pay more than $3 billion per year just to keep this plant running. And that's just in New York. Now, if we go to Atlanta with its power need of 2,934.03 gigawatt hours per year, we are going to need 51,997,691.24 meters squared of land. Now that's only like a tenth of the land we needed for New York. So now you can see in perspective just how much power New York needs and how big this is for New York. And so for Atlanta, the construction would be about 10 billion, still a very, very large number, $339,538,288. And per year, it would be about $410,768,200 per year. So, still a lot of money, but nowhere near New York. Chicago, it gets a little bit closer. With a power need of 10,820.69 gigawatts per year, we would need approximately 237,835,686.8 meters squared of land. And with that amount of land, there is about a need of 47,567,000. Oh wait, I did that wrong. It's actually $47,567,137,360 for construction and $151,489,660 per year. Whew! We're almost done with just CSP. Now to LA. LA needs approximately 9,349.33 gigawatt hours per year. Now, for that, we would need 154,224,624.9 meters squared of land. Now, For the money, we would need about $30,844,924,980 for construction and $130,890,620 per year. That is still a lot, but as I will get in later, LA is probably the best place for CSP compared to all the other cities because of how much land we would need. Now to PV cells. PV cells were a lot easier to find the approximate meters/feet. What I found was feet, and later I just converted it to meters. So I found that one full panel about 5.5 by 3 feet or 17.6 feet squared would give you about 265 watts per hour. So that equates to 1 square foot giving you about 15 watts per hour. Now I also found that the approximate cost of 1 square foot of PV cell solar panels is about $1.83 per square foot, and to keep it running is about 30 cents per kilowatt hour. What I calculated for the average power needs of New York, we would need about 59,498,380 meter squares of solar panels. Now compare that to the 559 million meters squared we would need of CSP. This is a very, very low number. It's crazy the difference I've seen between these two things. And then we get into installation and cost and prices per year. The original setup cost would be about $97,666,414.20 for construction. And then about $7,305,000. Oh no, excuse me. It would be about $7,305,665,000 per year. So you can see a dramatic difference between the cost per year for CSP and the cost per year for PV cells compared to the construction cost. Construction cost for the CSP is a lot bigger than the average cost per year. The average cost per year completely trumps the construction cost for PV cell solar panels. Now if we go to Atlanta, we would need about 6,636,968.75 meters squared of solar panels, and with that we would need 10,886,873.63 for the original cost to build these things and to buy them. That cost per year gets to about $880,209,000 per year. Still way bigger than the original cost. Now remember, all these numbers are between 2010 and 2015. When I was researching, the numbers have gone down a lot more for cost per year, so this is numbers for about 3 to 8 years ago. In Chicago, we would need about 26,721,823.40 meters squared of solar panels, giving us 43,864,059.01 for the original cost, and 3,000,000,000 $247,000 per year. Still crazy. I mean, these numbers are things we don't even think about. This is government money. We would be paying high taxes. But when you think about the electrical needs now, we're going to run out of that. Coal, other fossil fuels, they're not going to last forever. So we might have to invest in these types of things, and it might be necessary because it'll be one, renewable by the sun, which isn't really out right now, but we have plenty of, and these are big numbers, but so are the numbers today. This is per year. So do you think that it would be better just to pay a little more for solar power instead of wasting all of our beautiful resources? Sorry, just a little mini rant before I get to the final numbers of Los Angeles. For Los Angeles, now that we're there, we would need about 17,295,523.3 meters squared of solar panels, and that gives us $15,582,694.15 for the original cost. For the price per year would be about $2,804,799,000 per year. This is where I think that LA would be best to use CSP instead of PV cells. Let me tell you why. We see here that Los Angeles has an area of 1,303,000,000 meters squared. And to set up the CSP, we would only need 154 million meters square. That doesn't even put a dent into the area of Los Angeles. Plus, the price per year would be exponentially smaller than it is for PV cells. Now, let's look at New York, for example. With an area of 788 million meters squared, it would take about 559 million meters squared to put up CSP. Now, that is about 5/7 of the entire city of New York City. We don't have that. We've already built that. That is something we can't do. So this would be the time to invest in PV cells. It's very similar for the numbers of Atlanta and Chicago, but New York and LA are our two extremes, our extreme low and our extreme high. For Atlanta and Chicago, they are kind of blended in with New York in the fact that it would be better to invest in PV cells because we do not have the space for the CSP. Plus, in cities like Atlanta, Chicago, New York, when you think about these cities, you think of huge skyscrapers, especially New York City. You think of these huge skyscrapers that are very close together. So, if we think of that, let's just think hypothetically that the entire 780 million meters squared of New York City is all skyscrapers a couple 100 feet apart. If we think about that and we put solar panels on top of all those buildings, that would give us exactly what we needed. Every year we would have all the solar energy we would need, and we wouldn't need to go outside the city, for example, to set up these types of CSP. PV cells are just way more better for us to invest in than it is for us to do CSP, mostly because of the need for land. Money, we can invest in this sort of thing and it'll pay off in the long run. If we all do this, including cities and countries around the world, this cost will get a lot less because of the whole supply and demand sort of thing. These prices will drop like crazy. I bet you that we could get it down to like 10, maybe even 5 cents per kilowatt hour per year. If we just think about that, this could change a lot of things, and it would make the world a lot healthier place. Well, anyway, I hope you enjoyed my final project. It took a long time, but as you could see, I really got into the PV cells especially, and the prices. I really like to get in depth when I do something like this. And so I just really hope you enjoyed, and I won't see you next time because there won't be a next time. But I had a lot of fun in this class, and I can't wait to finish it up. Bye!